what we are going to start looking at today, and this will occupy most of our time until exam 3, well, half of our time, is how do you generate this magnetic field? And I hope as we go through this, you will start to notice some similarity to how we did things with the electricity. Like everything I do since yesterday and on, I'm hoping you are being reminded of what we did in electricity. But let me just start with so how magnetic field is generated. So for this portion of the course, I'm actually going slightly different order than what's in your textbook. If you look at Giancoli, this one is actually even in the asterisk section, and I never really understood that because this is the fundamental law. This is what you have to know before we get to Ampere's law next week. So the law we are going to go over is something called Biot-Savart Law. By the way, I'm just not going to know how to correctly pronounce this name. I think it's French, whatever. I'm just going to say, so the question I don't really know the answer to is whether to pronounce the T or not. So however you say it is fine with me, I'll just say Biot-Savart. So Biot-Savart's law, let me write down the form, and we'll go over each part of it in a little bit more detail. But let me first write it down so that you're not looking at a blank whiteboard as I'm talking. So it gives you a small contribution to the magnetic field at a given point in space due to a small section of wire. So small contribution to magnetic field due to a small section of current carrying wire. These symbols mean what they normally mean. I means current, like you have seen that. And DL means a section of a wire that I'm looking at. And the way this current that's flowing through this section of the wire is contributing to the magnetic field, it's given by this relationship. Let me write down the remainder. There's a constant of proportionality in front. And there's this cross product that I was telling you guys is in the law for generating magnetic field. R hat, it's the R unit vector. I will diagram it, but it's a unit vector. So this portion tells you the direction of the magnetic field divided by R squared. So some parts of this is kind of hard to visualize or it's a complicated expression. It has a lot of parts to it, and I probably should draw a diagram to illustrate how each of these quantities are defined. So this mu naught, by the way, so this is something called, I guess the more common term today is magnetic constant. But if you look at older textbook, this is something called the permeability of free space. So let me write it down. Permeability of free space. The gist of it is, it's a constant. You look it up. It's a number. It comes in some appropriate units so that everything works out. So I'm going to focus more on these portions. So let me draw a sort of a section of current carrying wire. Let's say I have a section of, I guess I'm actually not using green for the rest of today. So let's say I have a section of current carrying wire. So there's some current flowing through it. And let's say I'm interested in magnetic field at this point in space. Right? I mean, if there's current flowing through it, I skipped the whole introduction. Let me finish this, and I will talk about the introduction portion that I skipped. So yeah, let me finish this up first. So anyway, so you're interested in magnetic field at this point in space, and it's going to come from all the different parts of the current carrying wire. And let's say you are looking at this particular section of this current carrying wire. So using this diagram, let me illustrate each of these quantities. So the quantity dl, it's sort of what it sounds like. So the magnitude dl is given by the length of the segment that you are looking at. So that would be the magnitude dl. But you would notice I put a vector vector symbol up there. So I'm actually defining dl as that's my vector quantity. So it's a quantity that has this magnitude, and it points in the same direction as along the wire in the same direction as current. That's going to be my dl. And r is it's easier quantity to talk about. So I look at the distance between this segment of wire and the point where I'm trying to calculate the magnetic field. So that distance is what's called r. So this is r. And in fact, r hat is defined using this same geometric relationship. R hat is this. This is r hat. It's the unit vector pointing from the segment of wire towards the point where you are trying to calculate the magnetic field. Yeah? Okay, so sorry, I realized I skipped a whole section of the concept introduction before going into Biot-Savart Law. So I hope I didn't spoil too much. But here's the question that I should have posed and answered: what generates magnetic field? We talked about what is the fundamental unit of interaction if you already have the magnetic field. But we want to look at what generates magnetic field. And it's a very unsatisfying thing to say magnetic field comes from magnets. Well, where do magnets come from? Because we want to be able to break this down into very fundamental constituents. In our case, that would be protons, neutrons, and electrons. And we want to describe, we gave protons and neutrons and electrons an electric charge. That's how we describe their electric interaction. But they have no magnetic charge to speak of. So we want to be able to somehow get from an electric charge that's able to produce magnetic field. So this is where I would lean on accidental discovery, or I don't know, I keep saying accidental. It's not all that much of an accident because people were hoping to find this relationship, but they didn't know that this relationship existed. So you can, I hope it's in the textbook, but it's a discovery by a guy named I'm just gonna mess up all the pronunciations in this class. So Ørsted, I know how to spell his name. It's a discovery by a guy named Ørsted. Sorry, actually, I don't think I know how to spell his name. There's some grammar, it's Danish name or something. There's some marksum in there. I'm just gonna forget it. I'm gonna write it like it's an English name. So there's a discovery by a guy named that. So he was playing with currents using battery that has been invented not that long ago. I'm talking about like 1800s. So, this is what this is. It's a coil of wire. This is a power supply. It can provide current and voltage difference to this coil of wire to generate currents here. And what he noticed was that when he has this compass, that whenever current is flowing in this coil of, in his case, he was doing some other setup, but there's some wire that was carrying current. What he noticed was that when the current flows in the wire, that affects nearby compasses. So in his case, initial discovery was accidental, just playing with the electric stuff and electric circuit stuff. But this is a purpose-made device that's designed to produce set magnetic field. So when I turn this on, so right now this is the current control. Right now the current is off. I have two different positions of the switch so that I can turn the either current clockwise or counterclockwise around this loop of wire. So, this is what you can see. When I turn the current clockwise, then the compass turns in a particular direction. It forces the compass to line up. And in fact, when I turn this thing, the compass moves with it, indicating, there's a magnetic field that's making the compass move the same way, or be oriented the same way. And when I turn the current the other way around, then, okay, it was in unstable equilibrium. So, compass turns the other way around. And I can actually move this around to see how a magnetic field changes at different locations due to that coil of wires. So that's the discovery that was made. Once people figure out, oh, current is something that can produce magnetic field, then a bunch of people studied it. And it actually took quite a bit of time for people to figure out the exact relationship between current and magnetic field. And the reason why? Well, this is the reason why. It's a complicated relationship. It's, in fact, amazing that people were able to figure it out at all. Because when you have some current flowing through some wire, it's not the simple situation like with the electric field, where electric fields point away from the line of charge. It's not that. So, after some lengthy study by a bunch of smart people, they were able to boil down the relationship down to this basic law. Once you boil down the relationship to this basic law, you can actually begin to identify parts of it that maybe even looks familiar to what you have seen before.